In this project, we will simulate a three-phase flow fuel injector. A fuel injector is a device that sprays fuel into a car's engine using electronic-controlled valves, capable of opening and closing many times a second. They have an atomizing nozzle that distributes the petrol or diesel evenly for optimum combustion and efficiency. In this project, a three-phase flow fuel injector has been simulated by Ansys Fluent software. The standard K-epsilon model is used for flow analysis. The mixture of multi-phase model for three phases of air, liquid, and vapor has been used to investigate the phase interaction. The liquid will enter the computational domain through the injector with the velocity of 20 meters per second, and a jet flow is formed inside our computational domain. The geometry of the present project is designed in Gambit software. This geometry consists of a chamber and a fuel injector and an air entrance. The present geometry is meshed in Gambit software. The mesh type used for this geometry is unstructured, and the element number is equal to 932,107. Under the General Setup tab, you can see different buttons from scales to units. By clicking on the scale, a new window will appear showing you the domain extents of your geometry. Also, under the view length unit section, you can see the default geometry units, which is meter in this project. Also, under the scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh was designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. By clicking on check button, you will see that under the console tab, the Fluent software will start to check your mesh for any errors. Also, by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. By clicking on display button, a new window will appear which you can see different parts of your geometry. Now in the appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on display so that the software will show you that part. In this project, there are several assumptions taken into account. For example, the first one is that the type of our solver is set to be pressure-based since we are dealing with incompressible flows. As for the velocity formulation, we have taken the absolute format. And as for the time study, we have selected the steady time study since we didn't want our results to be a function of time. As you can see, in order to simulate and model different phases, we have enabled the multi-phase model. Under the model section, you can see that we have selected the mixture homogeneous model, and underneath it, you can see that we have enabled the slip velocity between different phases. Under the Phases tab, under the Phases section, you can see that we have added three phases of air, liquid, and vapor. Now adding another phase will be explained in the Material section in next slides. Now under the Phase Interaction tab and under the Forces, under the Phase Pairs section, you can see that for pairs of different phases, for example air, liquid, or air, vapor, we have the same force setup. For example, the drag force between these two phases abide the Schiller-Naumann correlation. Or for the slip velocity, you can see that we have selected the Mannion et al. Correlation for a slip velocity. After double-clicking on the Viscose button, a new window will appear. In the Appear window, you will see that we have chosen two equations, standard K-epsilon, to solve for our fluid flow. The standard K-epsilon model is one of the most renowned models for solving the turbulent fluid flows, and actually two equation K-epsilon model allows the determination of both a turbulent length scale and time scale by solving two separate transport equations. Now, as was previously mentioned in the mixture model settings, you can see that we here have three phases of air, water liquid, and water vapor as our main material for different phases. Now, in order to add a new material, you just have to right-click on Fluid and then select New. Now, in order to add a new material, all you have to do is to right-click on Fluid and then select New. After that, in the Appeared window, you either can define a new material by defining its properties yourself, or you can click on Fluent Database button and select New Material from the list of material available in the Fluent software. Now, after clicking on the pressure inlet boundary, you can see that the type of this boundary is defined to be pressure inlet. By clicking on Edit, a new window will appear in which you can change the settings for this boundary. For example, in the Appeared window under the Momentum tab, you can see that the pressure defined on this boundary is equal to 0. Now, in order to define what phase or with what velocity or what mass flow rates enter this boundary, you click on the mixture and then select, for example, the phase of air. After clicking on the air phase, you can see that the velocity magnitude of this phase entering our computational domain is equal to 20 meters per second. Now, if you click on the liquid phase in the Appeared window in front of the velocity magnitude, you can see that the value defined for this liquid phase has the same value like air phase. After clicking on the outlet boundary and clicking on Edit in the Appeared window in front of the gauge pressure, you can see that the value of 0 atmosphere has been defined, which means that our mixture flow will exit our computational domain to the atmosphere. Now, as for the wall boundaries, you can see that if you click on Edit button in the Appeared window, stationary wall motion along with no slip shear condition is defined. Now, as for the wall boundaries, you can see that if you click on Edit button in the Appeared window, stationary wall motion along with no slip shear condition is defined. After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first order event and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. After double-clicking on the Controls button, in the middle section of the software window, you can see that new part will appear. In the Appear part, you can see under relaxation factors for different parameters. Now, these values are set here by the software automatically. You can change these values, which are between 0 and 1, by yourself for different projects you do. But it is highly recommended that you do not do that, since it may result in divergence. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the 0, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the New, you are able to choose between different reports. For example, you can define a mass flow rate report on a arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence, but the residual must be checked as well. After double-clicking on the Residuals button, a new window will appear. In the Appeared window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than this criterion, it conveys the meaning that that equation has reached convergence. After double-clicking on the initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the compute from drop-down list and clicking on one boundary. For example, by clicking on compute from all zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. After double-clicking on the Run Calculations button in the Appeared section under the Parameters part by just defining the number of iterations and then clicking on Calculate button, the software will start the simulation process. Now in this part, we have extracted 3D and 2D contours by the means of CFD Post software. Now in order to extract a 3D contour, you just have to click on Volume Rendering button and accept the appeared window. After that, on the low left side of the software window, you can see that a new part will appear. In that part, in front of the Variable section, you can select your desired variable. For example, in this slide, we are going to select the liquid volume fraction. After defining the variable, by clicking on Apply button, the software will show you the 3D contour. Now in this 3D contour, you can easily see how the liquid has been injected inside our computational domain and how it has spread inside of it. Now in order to extract a 2D contour, we first have to define a plane. To do that, we click on Location and then select Plane, and then accept the appeared window. After that, on the low left side of the software window, in front of the Method section, we select YZ plane and set the X value to be equal to 0. And by clicking on Apply, you can see that a new plane is defined in the middle section of our geometry. After defining the plane, we click on Contour button and accept the appeared window. After that, on the low left side of the software window in front of the location, we select our defined plane. After that, we select our desired variable, which in this slide we are going to select liquid volume fraction again. Just like the previous slide, after that we click on Apply so that the software will show us this 2D contour. Now in this contour, you can better see the liquid volume fraction distribution in the middle section of our geometry, and you can easily see the liquid volume fraction has decreased near the interface of the phases air and liquid as it has turned into vapor. And finally, in order to extract the velocity contour, you just have to change the variable from liquid volume fraction to velocity. And just like the previous slide, by clicking on Apply, the software will show you this 2D contour. Now in this 2D velocity contour, you can see that a jet velocity stream has been formed inside our computational domain due to the injection process. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com.